Solve the following system of linear ordinary differential equation initial value problem. So we have dx over dt 5x minus y, and x at 0 is 2, and dy over dt equals 3x plus y, y at 0 equals negative 1. So we can write this system in terms of matrix notation. So in the left, x prime, y prime. X prime means derivative with respect to t. So here 5 negative 1, I'm just writing the coefficient, 5 negative 1 3 1 times x y. Okay, if you multiply, you're gonna get these two equations. That's the ordinary differential equation system, and we have initial condition x at 0, y at 0, 2 negative 1. Okay, like in previous question, we say this is A, and let's find its eigenpairs. That means eigenvalue and the corresponding eigenvector. Okay, so for this we do the following. We find the determinant of lambda I minus A, and we set this equals 0 to solve for lambda. So lambda I means lambda times I is, this is a 2 by 2, so identity matrix 2 by 2, 1 0 0 1, and when we multiply every single component, so we get this. This is lambda I minus A, means subtract this, minus 5 negative 1 3 1. When we subtract here, we just subtract component wise. So this is determinant of lambda minus 5, 0 minus negative 1, just 1, 0 minus 3, negative 3, lambda minus 1 here equals 0. Let's find the determinant, for we multiply this way minus this way. Lambda minus 1, lambda minus 5 times lambda minus 1 minus negative 3 times 1, negative 3. Okay, so FOIL, just multiply these two factors, lambda is squared minus 1 lambda minus 5 lambda minus plus 5 minus negative plus 3 equals 0. So lambda is squared minus lambda minus 5 lambda minus 6 lambda plus 3 plus 5 plus 3 plus 8 equals 0. It has to be 0, okay, in the right hand side. Now factor this. If it is not 0, we have to bring to the left in order to solve for lambda. Factor this polynomial, 4 times 2 8, 4 and 2 makes 6, so lambda minus 2 0, so lambda equals 2 and 4. Now for these two lambdas, lambda 2 and 4, we need to find the corresponding eigenvalue vectors. So let me erase this here. So let's find the corresponding eigenvector. Let's say V, just for lambda equals 2. So we go back here and solve this, lambda I minus A, V equals 0. So plug in lambda equals 2. So 2 minus 5, negative 3, 1, negative 3, 2 minus 1, 1. Okay, that times B unknown, that's the vector. Let's say V1, V2 equals 0, 0. And these two rows are linearly dependent. That will be the case every single time when we are trying to find an eigenvector, okay, in 2 by 2 case. So we can ignore the second, just multiply this row with this equals the first 0. Negative 3 V1 plus 1 V2 equals 0. So this implies V1 V2. So we can take V1 1, then this is negative 3 times 1 plus V2 equals 0. So negative 3 move over just 3, so 1 3. So we can find one of many correct answers in this way. Okay, so for 2 1 3 is the corresponding eigenvector. Now we need to do the same for another our eigenvalue, which is 4. Okay, so let's do for lambda equals 4. Again, go back here and plug in lambda equals 4. 4 minus 5, negative 1, 1, negative 3, 4 minus 1, 3. Vector, which is v1, v2 unknown, equals 0, 0. Again, these two rows will be linearly dependent, so we just take the first. Okay, let's multiply negative 1 times v1, negative 1 v1 plus v2 equals 0. From this we can find infinitely many correct answers, but just writing one of them. Let's say v1 v1, so this is negative 1 plus 1, so this will be 1. Okay, if we plug in 1 1 here, negative 1 plus 1 0. 1 3, if we plug in 1 and 3 here, we got 0. So 4 1 1 is the corresponding eigen pair. Then the solution, we can find the solution, not the final solution, but x, y, x is a function of t, y is also a function of t, equals c1 e raised to, look at the first, for 2 1 3, so e raised to 2t 1 3. In the same way, for lambda equals 4, so c2 e 4t 1 1. Okay, so this is the general solution, but we are given the initial conditions. X at 0 is 2, y at 0 is negative 1. Using this initial value, we can determine the constants c1 and c2. So this is x, means x at any time t, y at any time t. Now we take t equals 0 to apply the initial condition. So take t equals 0. So in the left now, x at 0, y at 0, we get that. And x at 0 is 2, negative 1, or here 2, negative 1. So x0 and y0, 2, negative 1 equals, we are taking t0. That means e raised to 0 is 1. So this is c1, 1, 3 plus c2 e raised to 0, because t0 means e raised to 0. That's 1, 1, 1. Now we need to solve this system for c1 and c2. And we go back and write down the solution. So here c1 goes on the top part, so this implies 2, the first component is 1, c1 times 1, c1 plus c2 times 1, c2. And second row, that's negative 1 equals c1 times 3, 3 c1 plus 1 c2. Okay, now solve this for c1 and c2. Okay, now we can use the method of elimination or method of substitution. c2, we can just use the method of elimination. Let me subtract second equation from the first. Subtract means we have to multiply by negative 1. That makes plus, minus, minus. It's gone. Then we have c1 minus 3c1, negative 2c1, 2 plus 1, 3. Okay, so 3 equals negative 2c1. That means c1 equals, just divide by negative 2, so 3 over negative 2. 3 over negative 2, which is negative 3 halves. Now plug in c1 in one of these two equations to find c2. So in one we have 2 equals c1 plus c2. c1 is negative 3 halves plus c2. Now we can isolate c2. So negative 3 halves, add 3 halves to the both sides. Okay, then we get c2 equals 2 plus 3 halves. 2 is 4 halves plus 3 halves, 7 halves. Now we do have c1 and c2 value. So the final answer is given here with correct values of C1 and C2. Okay, C1 is -3/2, C2 is 7/2. So thus the final answer, x is a function of t, y is a function of t, is equal to C1, which is -3/2, e raised to lambda was 2t, 1/3, plus C2, which is 7/2, e raised to 4t, and the vector was 1, 1. Okay, final.